my joke, but laughter really.
Good morning, everybody. Happy Monday. No? I actually was looking forward to getting to work today because my weekend, I mean, it wasn't terrible. Nothing terrible happened, but it kind of sucked. Plans that I had put together between January and May, other people that had procrastinated decided to change everything, and I had no power over it, and I got to deal with all the consequences. So, it always seems that when I'm being proactive and I plan ahead, I get punished. Anybody ever felt that way? Yeah. You get rewarded for procrastination? I hate that. So yeah, I look forward to getting back to work today because this is better. Let's see. There were questions about the lab that's quote unquote due tomorrow. We're going to work on that last problem together. We just are. So that's part of what's going to happen tomorrow in lab. Okay. We're going to learn more about integration today, and it's going to bleed into tomorrow. Chapter 22 might start today, but more likely on Wednesday. Some of you have sent me emails panicked about the homework. I don't understand anything. It's because I really haven't gotten it. We're going to get into the meat of it today. Okay. I lied to you last week and I didn't know it. Were we talking about in one of the lab sections? Were we talking about physics 4A and 4C and 4B in the order that they're given at Fresno City College? Like you can take 4B and 4C in any order. I know you're in 4B now, right? Mm-hmm. But technically, so I didn't know it till Friday morning. But as of next semester, Fresno City College is going to offer physics 4A, 4B, and 4C every semester. I will not be teaching 4C. I will be teaching 4B again next semester. Okay? So just so you're aware, this affected the 4A students, I think, more than it affected you, because we usually have to tell them to go somewhere else in the spring to get 4B, but we can keep you all here now. The new science building is giving us flexibility to be able to do that. So. I will not be teaching 4C this year. Not yet.
Does that mean you guys are going to alternate how many classes you have of 4B and 4C each semester? You made it sound last
It's a really good question. No, I think we are increasing.
Just overall? Cool.
Yeah. If anybody knows any physicists that need a job, we've got the faculty to cover everything from our current faculty, but it's tight. Yeah. So the other bad thing is that the 4B class next year is got a Monday lab. I'm going to be teaching from 9:30 to 5:15 on Mondays. You guys know 9:30 a.m. to 5:15 p.m. And anybody, you don't know me probably well enough yet, but you should know that I turn into a zombie after 2 p.m. I'm a morning person. And in our house, we call that period between 3 and 5, we call that arsenic hour. When we had little kids, it's just the time when the kids just fall apart because they're hungry and tired and poopy and whatever's going on. And arsenic hour was you wanted to take it or give it. It was one of those two things, right? Because it was just that bad. So, yeah, it's going to be interesting next semester. See how I do. I'm probably going to end up in the fetal position under the lab tables. At 3 o'clock in the afternoon. 4B, 4A, 4B is what I'm teaching next. I didn't know that till Friday morning. I got the new schedule. I was like, this isn't right. We don't teach 4B in the spring. And we do now. I was game on. Told you about the lab. COVID. Your classmates have been emailing me. Some of us are not here today because they have COVID. Just letting you know. It's coming up. We got immunodeficiencies in my house. I don't like wearing it while I'm lecturing because as soon as I put this on while I'm lecturing, people stop looking at me and paying attention because I'm not human anymore or something. I don't know, right? But if you come up to me and ask me a question, and probably most of the time in lab or something like that, I'll have my mask on. Don't be offended. It's not you, right? But I'm just letting you know, people are coming down in class, coming down with it. Thankfully, mild cases, right? But CDC guidelines are still to isolate until you are feeling better and don't have a fever. Like, you don't have to be completely symptom-free anymore. As long as you're feeling better and don't have a fever, wear a mask for 5 days. That kind of stuff. So, and please, if you feel like you want to wear a mask in here, please do, right? And if anybody gives you trouble for it, tell me, I'll kill them. All right. Because I like masks. Masks say, don't talk to me. I don't want to talk, yeah. All right. Roll sheet. This is the roll as of this morning. Like, I fresh downloaded from this, so I probably screwed it up somehow. Luis, say hi. You're in the first one, right? Keep picking on Luis. Is he here? No? Let's see. Luis Jimenez. You're in the 8 a.m.? Yeah? Yeah? All right. Okay. All right. So, go back, fill out last week and today. All right. If your name is not on there, there's a problem, like a big problem. We need to solve it right away. So come up to me after class. We were here last time. We were talking about R vectors, right? And all that kind of stuff. So what are we trying to do? We are trying to find the net force, okay, on, I shouldn't write it that way. We're trying to find the net force on charge number 3. That's what we're going to go for. We got 2 charges. They're pushing and pulling on charge number 3. We are going to find that net force. And the way we're going to find it is we're going to find the 2 forces that are acting on charge number 3. The subscript notation, right? The thing that's causing the force, the thing that's experiencing the force. Notice how both of them end in 3s, right? Because we're trying to find the force on 3. If we can ignore charge number 2 for a second and just concentrate on 1 and 3, that's F1, 3, find what that vector is, and then find the force vector, ignoring charge number 1, just from 2 and 3, and we put them together, then we can find the total. This is our common approach. Did this way back with Newton's laws. Anytime there's a force, right? You got multiple things pushing and pulling. You isolate the 2 things that are interacting, do that one, do the next pair, do the next pair, and then you bring it all together at the end. It's just now we're going to do it with Coulomb's law for the force, right? And Coulomb's law states that there's a constant, 2 charges, a distance between them, and then this r hat vector. But I'm going to switch this to a method that's got an r cubed in the bottom with an r vector. And just trust me, you're going to want to practice and kind of get familiar with this r vector because it's going to keep coming up during the semester. And help me remember what the r vector means. So if we're going to find, we'll do 2, 3 first. It might be a little bit more straightforward. F2, 3, okay? We want to find that force, okay? We need to know several things. We need to know the charges, we need to know the distances, we need to know all that stuff. For those of you that are keeping track at home, I didn't put it on the screen for some reason, Q1 and Q3 are both 5 microcoulombs. That little funny mu right there means micro. Charge number 2 is -2 microcoulombs, and all of the distances are 1/10 of a meter. So that would be the numbers we're eventually going to put in. Okay, so to break this force down, I need to know some things, right? What do I need to know? So this is going to be equals K, my electric force constant, which is just a number, okay? And then what are the 2 charges that are what's the first charge that goes in here? Based on just the subscripts alone. It's going to be charge 2 multiplied by charge 3. I hope you see that there's like a systematic way that we're doing this, right? the distance r23 cubed r23 vector. Very little thought has gone into what I've just written down. I'm writing down Coulomb's law specifically between charges 2 and 3, and really just kind of copying my subscripts through and setting up the calculation that I need to do. In order to be able to do it, do I know that constant? Do I know K? Yeah, 8.99 times 10, whatever, right? Do I know charge 2? Given. Do I know charge 3? Given. Do I know the distance, R23, the distance between Q2 and Q3? Yeah, right? Okay, it's A, or 0.1, right? Okay. Do I know the vector R23? Yeah, we did it last time, but let's do it again. Right? So right here, I want to say, what is the vector R23? R23 equals, and where does it start? Look at the subscript notation. Where does it start? It starts on 2. Where does it end? On 3. Draw it. Right? R23 is right there. Actual physical vector, right? Don't have to figure out what R hat is or that kind of stuff, right? So R23, what is it? Like if we wrote it down in unit vector notation, it's pointing in the positive I hat direction, isn't it? And what's its magnitude? Yeah, A, or 1/10 of a meter, right? Okay. So my vector is A I hat. That's what my R23 vector is. What's its length? We're asking all the same things over and over again this way, right? Okay, but that's good, right? Repetition, getting the same answer out means you're probably doing all right. Okay. So now I can write down what F23 is. It's K, Q2, Q3 all over A cubed times A I hat. Simplify that a little bit, and what happens to one of the A's? Cancels, right? Cancels with that one, and I'm left with K, Q1, Q2 all over A squared times I hat. Now, Mr. Baylor, I could have guessed that the R hat vector was pointing in the x direction. Oh, sure. Simple diagram. But what happens if you've got 3? What happens when we do charge 1 and charge 3? What happens when we have a quintillion charges? What are you going to do then? Cry. Because you got to put all this in an integral. And then good luck guessing what R hat is.
So one of them is Q2, Q3, and another one is Q1, Q2?
Yeah, we haven't gotten to that one yet. Q1 and Q3.
They're two different
Yeah.
things.
Yeah, because what we're doing, right, is Q3 is what we're after. Q3 is like being pulled this way and pushed that way, right? So we've done this first vector. We're going to get there. That's 2, 3. And then we're going to go find this one.
That's what I said.
And that's going to be F1, 3.
No, on the bottom.
Oh, here? Yeah, this is F2, 3. I decided to do this one first.
But in the equation, it's Q1, Q2.
I'm so sorry. It was right in my brain. Just not on the page. Thank you. Q2, Q3. Are we good now? I should pay more attention. I'd like to blame that one on getting old, but honestly, I've been doing that the entire time. Even through college. All right, so numbers. I'm just going to put numbers in this one. 8.99 times 10 to the 9. Okay, the reason I'm going to put numbers is because I want to demonstrate something for you. What am I going to write down for Q2? What is the charge on Q2? -2. If you are going to use the R vector method, you want to put the sign of the charge into your calculations. If you're going to do the books method, what they have you do is figure out the directions based on opposite subtract and like Chappelle and some stuff like that, okay? It's a fine method. It works just fine. I'm just warning you right now. R vector always points from the thing making it to the thing feeling it, and then you use the sign because we know what Q2 and Q3 have to do, right? What do they have to do? What direction is the force? Towards each other, right? Well, our vector, R23 is pointing that way, right? We need the force on charge number 3 to point the other way, don't we? That's the negative sign on the charge is going to help there. Okay? So we're going to include the negative sign using this method so that the R vector can do its magic. So negative 2, what?
Times.
Good. Times 10 to the minus 6. That's what that micro means. You got to get it in there. For Q3, it's a positive 5 times 10 to the minus 6 coulombs. And then my A is 0.1, and that gets squared, and there's an I hat on there. Then we would calculate the number, and we would get it, right? Note it. Check it. What direction is the force on from charge 2 on charge 3? When we do all that number, what are we going to get for the direction? A negative I hat. Which way does that point? To the left. Should charge 3 be tugged to the left by charge number 2? We're golden. Okay. Let's do F13 now. Slightly harder because angles. Okay. What do I need? I got K, Q1, Q3. Did I get them right that time? R13 vector. So this means I need my R13 vector, right? What does R13 look like? Well, where does R13 start? Starts on charge number 1, ends where? Charge number 3. R13, right there. You can draw it right on the diagram. Okay. Can I write it down? Like what it actually is? I could write it like that angle is 45, right? So I could write it that its length is something at 45 degrees, but we really want to get this into x's and y into Cartesian coordinate, right? So do we know the pieces parts? Do we know the components of R13? Do we know how much it points that way and how much it points that way? What's the length of the x component? A. What's the length of the y component? A. So we can just write down A positive I hat. R13 points positive x and then positive y plus a j hat. Okay, that's my vector. How do I find the magnitude of any vector? Square the components, add them together, square root, right? So the length of R13 is going to be the square root of a squared plus a squared, which is the same as a times the square root of 2. You're like, well, duh, Mr. Bay, that's a 45-degree right triangle. Of course it was that. What if it isn't? Right? What if your components are a I squared minus b j squared, right? Like, what if they're different? And it's not a 45 or a 60 or anything else, right? You can just write down what they are and then find the magnitude. I'm giving you a crank to turn, right? You've got to be careful about signs on things, but you really don't have to be all that bent out of shape. If you nail your R vector and you nail the signs of the charges, it's going to take care of everything else for you. It's a little bit like magic. All right. So we've got the magnitude, we've got the vector. So that means F13, that force, is going to be K, Q1, Q3, all over A times the square root of 2 cubed times A I hat plus A j hat. And now that F13's got 2 terms. And should it have 2 terms? Does that force point in both the x and y directions? Yes. Okay. Looking forward, I'm not going to put the numbers in. Both of these charges are positive, aren't they? You want to get through both positive. This is just a number. That's all positive. So this force is going to end up positive. Q1 and Q3 have the same sign of charge. So which way does the force point on charge 3? Points away. And does that thing look like it has both positive components? Looking good. Okay. So that's the method for dealing with collections of charges. In this chapter, we give you 2, 3, or 4 charges, ask you to find the charge on just one of them, okay? You can use the books method, which is more like what we did in chapters 5 and 6 from Physics 4a, or this newer method that I'm showing you where we do our vectors. And we use the signs of the charges. It's your choice, you don't have to do it this way, but this method's gonna come back a lot, okay? And especially when we get to magnetism, we're gonna need to use the R vector in its full glory. And in the long run, this keeps track of stuff for you. There's fewer mistakes to make, fewer things to remember in this method than finding vector components and their directions and things like that. So you choose. Either way, I'll be happy. I can read both ways. Just in case you're curious, what I got was that F23 was equal to -9 I hat. And then when I put numbers in here, F13 was equal to 7.9. That's a 7. That doesn't look like a 7. 7.95 I hat plus J hat. Okay, so we get those numbers. We're not done yet, right? Those are the two separate vectors. What do we have to do with them? Add them all together. How do you add vectors? X component plus X component, Y component plus Y component. And what I got was that F3, the net force on 3, was a -1.05 I hat plus 7.95 J hat. And of course, if I wanted to know the angle and the magnitude, find the magnitude, square root of the thing squared, angle would be the inverse tangent. No! How are we doing?
Probably missed it, but why do we for force of 1,3? Why do we cube the denominator compared to like?
We cube the denominator because I, number one, forgot to write down the cube right there. Okay, the cube is coming from using R vector instead of R hat. Okay, I'm substituting in. I showed it, I think, last time, right? That when you a unit vector is the vector divided by its magnitude. And what I'm trying to show you, and I hope I can convince you a little bit, is that it's easier to find our vector than it is to just think about where R hat is. Like, what's R hat? Where's that pointing? You know, like magnitude 1, what does that mean, right? But our vector can often just be read right off your coordinate system. Did I answer your question?
Yeah.
Maybe? Okay, yeah.
I think he's more asking when you were doing F23 because you canceled your cube with the A in your I hat to make it a square.
Oh, yeah. I mean, just because I had an A upstairs and I had an A downstairs. That's just algebra, right? I can't do that right here. Well, I guess I could. I could factor this A out and then cancel one of the A's right there, right? But I have a factor of √2 floating around.
Where did that 7.95 come from? I kind of zoned out.
I don't blame you. It came from me putting all of these numbers in here.
Okay.
I often don't show that because it's a waste of time as far as I'm concerned. I mean, it's important, but like we've got better things to do in class, like answering your questions. Any others? Okay. I want you to turn to each other. I used to make this a quiz, but I'm not going to make this a quiz. Okay, because it's me. I want you to turn to each other. I want you to work together on plotting. Well, let's just plot them together. We'll do that part together, okay? So an electron. Oh, that's important. Since it's an electron, what charge is it? 1, 2, 3, 4, 5. 1, 2, 3, 4, 5. There we go. Okay? That's a negative charge. That's an electron right there. Okay? No net force when a charge of positive Q is located at 640. So 640, positive charge, sitting right here. Okay? Plus Q. Right? Then we have another negative charge that is located somewhere. Right? What I want you to do is find out where to put the negative 4q charge. We want 0 on that electron. Where do you put the negative 4q charge? This can be done with no math. There's an easy way and a hard way to do this problem. Turn to each other and see if you can't figure it out. Go. I did this backwards. 6, 4 would be right here. Thank you.
There's no net force and it has to cancel out. Already exists. Right? So this would show like already exists and then you that means it has to be pulling in the opposite direction of where that positive charge already is, right? In order for this to
All right.
and then it has to be
Does anybody think they know the answer? Yeah? Give it a shot? 7, 3? Okay, so make sure I do this right. 7, 3 would be like right there? 3, 7. Right there? No, wait, 3, 7 would be right. Where's 7? 1, 2, 3, 4, 5, 6, 7. 1, 2, 3, 4, 5, 6, 7. So you're saying 7, 3. 7, 3 would be like right there. Does anybody else agree with that spot? No. No? Okay, where do you think it is? No? Really? 1, 7, 8, 9. Somewhere like right up in here.
8, 2.
8, 2, like right there. There's a theme emerging with these guesses, which I'm actually quite glad to see. 3, 7. Okay. So like right in there, right? What's the theme that is emerging with all of those answers?
Keeping it all on one axis.
Ah, this is really a one-dimensional problem. And that's kind of the trick, okay? Because those forces can only be towards and away, right? And our vector, our hat vector, it's either towards or away. And so what you want to do is you want to try to think of like a dotted line that just, the charge has to lie somewhere along that line. Because if it's anywhere else, like if the negative 4 charge, I don't know, is sitting right here, okay, it's going to push away that direction, but the positive one's going to pull it that way, right? Can you get 0 net force with 2 vectors that have any angle with respect to each other? No, it's impossible, right? We need our vector forces on this thing to be opposite each other, okay? So the positive Q charge is causing a force what direction on this electron? Towards or away? Towards. It's pulling this way, right? So that means we need an away force pointing that way. So what's the only place now, north or south, okay, that we can put a negative 4 charge to have an away vector? It's got to be down in the south, right? If we put a negative charge up here anywhere along this line, it's going to cause a vector pointing that way, isn't it? And then we'll have two vectors pointing that way. That's not zero. But a negative charge anywhere along here means that that force vector will be pointing that way, which is the way we want it, right? Okay, so now we know that it has to be somewhere south on this dotted line. The question now is where? It's a -4 charge. There's a clue there about the distance. Not 4 times the distance, twice the distance, right? Because it goes as r squared. It's an inverse square law. So how far away is the positive charge from the electron? Kind of 1 unit, 1 diagonal, right? So we need to get it 2 diagonals away. So if we put the -4 charge right here, okay, it ends up being twice the distance away, which would end up being a 4th as strong to compensate for the 4 times bigger charge. What? Go back, review that, okay? See if you can't catch it. We are taking advantage of Coulomb's law, where it's the product of the charges and the inverse distance, right? Directions we handle by looking at the forces, and towards and away. And then the distance, that inverse square law. We end up with a 4QQ on top. QQ, that's what you're doing right now, right? And we need to cancel the 4 with a twice the distance in the bottom. So that those 4s cancel each other out. Got real, didn't it? Gets real quick. Okay. Your book chooses to offload this into chapter 22. I want to start it now. So this is a bridge. So your book will kind of tangentially mention that you can integrate to find charge, but they do it in the context of finding electric fields. And I think what I want to do is I want to expose this to you because this is going to inform tomorrow and working on the problem that we're going to work on tomorrow. Okay, that last problem in the lab. And I want to prototype for you what I started doing last Tuesday when it came to thinking about integrals and integration and all that kind of stuff, kind of those densities that we had. And so let's start. Let's start at the very beginning. Very good place to start. Does anybody want to start singing? Do you know the sound of music? Do I need to assign homework? Not everybody's a musical buff like me. All right, that's fine. Let's, you know what? Let's not do that. Let's, oh, I did have a line of chart. Look at that. I already drew it. That was smart of me. Thank you, pass me. That was great. Because then I don't have to afflict you with my very bad drawings. Okay, so let's say I got a line of charge right here. Okay, it's just a rod. Maybe it's a conductor. It's got charge on it, and we're gonna assume, okay, for starting off very simply here, that the charge is uniformly distributed, meaning it's the same everywhere. Okay. I want to demonstrate how to integrate to find the total charge on it. That's the goal. The rest of the day is all about finding the amount of charge on an object depending on where that charge is and what it's doing. So we're going to do that by integration. And I showed you last Tuesday kind of where to start. If you're trying to find the total charge, what do you write down? I think we did it with mass on Tuesday. But where do you start when you're just totally lost and you're asked to find what's the charge on that rod? This is not a good sign. I'm not explaining it clearly. You start with what you want. What do you want? Total charge. Big Q. Right? Q, big Q usually means total charge. Little q means a little piece of it. Okay? That's what I want. And I'm going to find it by adding up all my little pieces of charge. Am I doing anything magical right now? No, this is just a different language for what I just said. I'm going to find all the charge on the rod by counting all the little charges on the rod, add them all up, I'll have the total, right? Okay? If you want to find the total number of apples in your basket, what do? You count up the apples, adding together until you're done, right? So that's what we're doing here. And that's the statement I made. And this is where your brain needs a hook. It needs to get started on something, and it needs to know where it's going. And so you say, I'm going to find the total charge, and I'm going to do it by integration. The magic comes from figuring out what that dq is. That's where the rubber really meets the road. And I gave you a tool last Tuesday for connecting things like physical parameters of the universe, like charge and mass and all that kind of stuff, with coordinates. Do you remember what it was? It's density. This concept of density, you're like, Mr. Bailey, what does charge have to do with density? Density doesn't just have to be mass per something. It can be charge per something. And so we can define a linear charge density as a Q over an L, a total charge divided by a total length. We can do a surface charge density, where it's going to be the total charge divided by the surface area. And then we can do a volume charge density, where we take the total charge and divide it by the volume. Like mass, charge, it's a real physical parameter, but lengths, areas, and volumes are talking in the language of a coordinate system. Points in space. And this concept of density, not just mass density, but charge density, peanut butter density, squirrel density. You can find the, right? How many squirrels are there in the park? Find the squirrel density. It's the number of squirrels divided by the volume of the park. Whatever. Okay? This concept of density can get blown wide open. It's not just mass. It allows us to connect things. So, how do I find a little piece of mass? If I know that I have a total mass charge, how do I find a little piece of charge? I look at my total charge divided by my total length. And the ratio, because it's a density, will stay the same. If I take a little piece of charge, I have to take a little piece of length. That ratio stays the same, especially if I have what's called a uniform charge density. If I don't have a uniform charge density, I've got to go find out the function, but it'll still hold. Now, instead of a length, since our rod here is stretched out along the x-axis, what direction am I going to go? In the x direction, so we'll just swap symbols. That's all it is just a symbol swap. If the rod were lying along the vertical axis, what would you put? dy, okay? All right? But I still don't know what dq is. How do I find dq? Yeah, well, lambda is equal to dq over dx. That's not a derivative. It's a ratio. It's a density. And so I multiply both sides by dx, which means that my dq is equal to lambda dx. And now I can insert that in there. It becomes the integral of lambda dx. And now that I've got coordinates down, I can put limits. Technically, I can put limits on the first one. It's kind of easy. from 0 to total charge, but that's kind of pedantic. Okay. what are the limits here? Where do we want the integral to start counting charge, and where do we want it to stop counting charge? Wherever it starts, wherever the rod starts, to wherever it ends, right? So if this rod had a length L, whatever that length is, I would go from 0 to L. What if it wasn't located at the origin? What if the rod was offset and started at 3 meters and ended at 5 meters? What would you put? 3 to 5. Okay? All right. I now have an integral with limits and an x or a y or a z, something that I can actually do, right? So how do I integrate lambda dx if lambda is a constant? Okay, right? Lambda comes out. The integral of dx from 0 to L is going to be lambda x from 0 to L. I put in L and I put in 0, and what do I get? Lambda L. What's lambda times L? It's Q. What the heck? Mr. Balogh, you started with Q and you ended with Q? Yeah, I did. Mr. Balogh, why did we just waste time on it? It's not a waste of time. I wanted to teach your brain a thinking process. Think about what we just did. I said that I want to find the total charge on a rod. The charge is uniform throughout all that rod. If we take the total, if it's 10 coulombs, I don't care what it is, it's 10 coulombs, and I bust the rod up into 10 equal pieces, what will each piece have on it? 1. And if you add 1 up 10 times, what do you get? 10! This is not advanced mathematics, right? But it feels like it. It's new. You haven't seen stuff like this before, right? And this was the very, very first baby step, right, into thinking about what's going on here. We literally just said, look, I'm going to find a little piece of this rod. I'm going to locate it at some variable x, and then we're going to let the integral do all the addition for us, right? And it should come as no surprise. We have a uniformly charged rod, 10 microcoulombs on it, and we do all of this stuff, we should end up with 10. So why are we doing that, Mr. It seems really stupid. We know it's 10. What happens if it's not uniform? What if this is an insulator and the charge varies from place to place? How do we do that? So if we know that the charge density varies and goes as some constant times the cube of x. How do we now figure out what the total charge is? Where do we start? What we want. What do we want? How do we get it? Isn't that the chant you do in sports or whatever? Or when you're protesting something? What do we want? How do we? Okay. We're going to add up all the little DQs, right? We know what DQ is. Does it matter if it's uniform or not uniform? Is density density? Yes. Okay. So we know that our DQ is lambda dx. We're still going to go from 0 to L, whatever that length is. But now we can drop in what that non-uniform charge density is. And then we can integrate. The A comes out. We're integrating from 0 to L, x cubed dx. What's the integral of x cubed? It's going to be x to the 4th over 4, right? From 0 to L. So this is going to be a L to the 4th over 4, whatever that number is in coulombs. And all of a sudden, something that looks like a big chore, like Huh? This thing changes its charge by x cubed? It means like there's no charge on the left end, and then there's just a ton of charge on the right end, right? Okay? How? Because we have a method, a systematic approach to being able to find what these charges are. But that's just one dimension. We've got 2 and 3D charge densities. So when we do linear charge density, we end up with how many integrals? One. And those of you that have taken Math 6? Oh, when you're doing surface areas, how many integrals do you need? 2. Kill me now, Mr. Van. And if we do volumes? 3. The answer in physics 4B is we only ever do 1. Huh? Wait a second. How do you do a volume or surface area with only 1? I'm so glad you didn't ask. Let's do volume first. Volume, I think, is a little bit more straightforward, okay, than surface areas. Let's suppose, for the sake of argument, that we have a volume charge density that is given as some number times r squared. Let's stop for just a second, okay? We have a charged object, okay? And they're telling us that it goes as AR squared. So what does that mean for how charged it is at the very center? When R equals 0, or the center of the spherical object, how much charge do we have? None, right? There's no charge in the center of this object. But as we go outwards, what's happening to the amount of charge? It's increasing. It's getting bigger and bigger and bigger. It's not uniform throughout, meaning the same. It means that it starts at 0 and goes as the square as we go out, right? Okay. We want to find out how much charge is in this object that follows a rule like that. Okay. And the nice thing about our rule, the charge density, is it has a symmetry to it. It only changes in one dimension. Now, all of you are, you have to be enrolled in Math 6 right now, or you need to have taken it. But when do they introduce you to spherical coordinates? Is that Math 6? It's Math 6, isn't it? Okay. So why am I going to talk about it right now? Well, I kind of am. Spherical coordinates are a way, kind of like Cartesian coordinates, cylindrical coordinates, right, of talking about what's going on. The nice thing about cylindrical and spherical coordinates, even though they feel weird and you're not used to it, is they're like the natural language of symmetries. Okay? If you go to a foreign country, sure, most people understand English across the world, right? But you can really understand what's going on if you're speaking their language, right? The same thing happens when we have spherical or cylindrical systems, right, where they just lend themselves better to speaking in that language. That's why we'll use that coordinate system. So on a sphere, you can figure out where you are. You know how far away from the center you are, how far kind of north and south you are, like kind of like a latitude, okay, on planet Earth, and then like a longitude, an angle that goes around, okay? That's sort of the general concept of the spherical thing. But as I can look at my charge density here, there's only one direction that matters that this thing is changing, and that's the outwards direction, right? No matter where I rotate myself, it's going to be the same because there's no other angle in there that it depends on. It only changes in the radial direction. And for those of you that have had Math 6 and you're panicking, oh my gosh, what are you going to do if you do both? We don't do that. This is how we're going to get around and only ever have to do one integral. We want to find what? We want to find the total charge. That's where you start. We're going to find it by adding up a bunch of little charges inside of this spherical thing. right? We're going to break the spherical thing up into little chunks. Just like we did the rod, we broke it up into little chunks of charge. We're going to break this thing up into little chunks of charge, and we're going to teach the integral how to add up over all those little chunks. In Math 6, I'm going to guess that they taught you to break those into like cubes. Did you guys ever do that? You little X, Y, Z little cubes, and then don't break spheres into cubes. Spheres are not cubes. No matter what the mathematicians say about infinite radius, whatever, right? Spheres are not cubes. So, what we're going to do is we're going to try to break this up cleverly so we only have one integral to do. What do I mean by that? We got to find dq, right? We're going to use density to find it. Charge density would be total charge divided by total volume. So if I want to find dq, I take a little piece of the charge and a correspondingly small piece of the volume. And then I can rewrite, right? I can just do a little bit of algebra to solve for that dq. And now that dq goes up into here. And I have an integral of my charge density dv. Are you okay up to this point? Am I showing you really anything new up to this point in the math that I put on the screen? This is identical to what we just did with the line. It's just instead of a dl, we have a dv, don't we? And so again, here's where the rubber meets the road. This is going to be the hard part, the conceptual heavy lifting and figuring out what's going on. We want to find a clever dv that lets us take advantage of our density function, but also avoids having to do a three-dimensional integral. And because this density only changes in the r dimension, the radial, the outward dimension, we are going to try to bust this sphere up into chunks of volume that only change in the radial direction. That's a clue. The clue is I want to change in the radial direction. Just like with the line, I knew my dl had to be dx going along that line. What do you think my little d is going to be in this problem?
Yeah.
It's r. We want a dr eventually because our function goes as r squared, right? So we know we want to integrate over the radial direction. The question is, how do we get there, right? My dv, I got to figure out what this little piece of volume, like the volume of a sphere is what? 4/3 pi r cubed, right? Okay. However, volumes can be thought of lengths and widths and heights, right? Okay. So the question is, how do we cut it up? I've had a picture of an onion on the screen the whole time for a reason. Because an onion is an excellent, excellent example of an ogre. Ogres are like onions. Okay. Layers. The individual layers of an onion represent a differential volume of the whole onion. What the heck just happened? This is not cooking class, this is still physics. If I can find the volume of one of the layers of the onion, and then find the volume of the next layer, and find the volume of the next layer, breaking my onion up into each of its individual layers, and I find the volume of each of those and then add them together, what do I get? The whole volume. So cutting a sphere up into onion layers is a really good way to be able to take advantage of what we call radial symmetry. Okay? Nothing else is happening in any other direction in the layer. It's only the outward part. So I've got another picture down here, okay, which is sort of like I've cut the onion or the sphere, I've cut like the top off and we're looking down at the top, okay? So if we cut that onion in half, right, and we're looking down on these layers, right? That's this picture right here, okay? We're going to see these rings heading outwards, aren't we? And so if we can find the volume of just this little ring right here, we are golden. I know I want to bump out in like the width of the layer. I want to go out in the R direction. So I need to find the thing that's constant around that ring. Yeah, surface area. My differential volume is going to be a constant surface area times a dr. So now the question becomes, what is the surface area of a sphere? Hey Siri, what's the surface area of a sphere? 4 pi r squared. How do they know that? Because Siri knows. So 4 pi r squared. That is the surface area of the, like that inner surface, right? And then to make it a volume, how do I make a volume out of a surface area? Multiplied by another dimension, right? And that other dimension we're going to multiply by is dr. If you wanted to set up the triple integral in theta and phi and r, you would find that as soon as you integrate theta and phi, talking to math 6 students, right, you would end up with a 4 pi r squared. That's what you get, surface area of the sphere, okay? We're avoiding that because we just conceptually are going to go, okay, surface area of the sphere, onion layers. Onion layers are the surface area of the sphere bumped out, right? To get a volume, I find the surface area and, right? Think of a basketball, right? A basketball, you could take the inner lining of where the rubber starts, find that surface area, then multiply by the thickness of the rubber, and now you've got the total volume of that shell, right? Okay. Our little dr, though, is going to be infinitesimally small, isn't it? In the magic of an integral, it's going to put in the limit of the minute, and then it... That's technical math speak for what all happens in there. So that dv is going to go up there. And what are the limits going to be? We are doing dr. It starts at 0 and it goes to where? Whatever the radius of this thing is. Wherever it stops. Wherever the physical object stops. My head hurts. There's no possible way I could have known this. I'm doomed. Okay. The second part isn't true. First part is. Probably the first time. Is this the first time you've seen anything like this? Probably. Okay. I say it a lot, and it's kind of a joke, but it's not. Knowing is how you know stuff. Sometimes you just need to be exposed, right? To an idea, a way of thought. And so now you know. And now you need to practice being clever, right? About how you pick stuff. But there's some checks you can do along the way to make sure that you're doing it right. Look at the units of your integrals. Is 4 pi r squared dr a volume? Does it have units of volume? What are the units of 4? No units. What are the units of pi? No units. What are the units of r squared? A length squared, right? A meter, think of it as a meter squared. And what are the units of dr? A meter. Is a meter squared times a meter a volume? Chances are, if your units are correct, you're on the right track. If we ended up with a meter squared or just a meter, something has gone terribly wrong because we're no longer integrating over volume. I think I told you this, right? Some people come up to me and I can tell instantly that the integral's wrong because I look at the units, right? I can tell something's wrong because the units aren't right. So check your units, right? We still have charge in there because it's a charge density times a volume, and a charge density times a volume is a charge. So we're good there, right? But now that we have, I mean, that was a long fight to get from this to this, wasn't it? Right? Some sort of magical witchcraft happened somewhere in here that some of you are still looking at, like, oh, what is going on? It's okay. We're going to do this a lot, okay? Over the next couple of days, this is going to happen a lot. And then it's going to happen a lot with electric fields, because we do this trick with electric fields. And then it's going to happen a lot with electric potential. We're going to do electric potential. And then we're going to take a break from it and do circuits. And then we're going to come back and do it a lot with magnetic field. You're going to get this a lot. A lot. Okay. So now we can do an integral, right? So this charge is now the integral from 0 to r of AR squared. That's what my charge density was, times 4 pi r squared dr. Okay, I'm integrating now. I can turn off physics brain and turn on math brain. What are some constants?
4a pi.
Yeah, the 4a pi, right? So let's get those out. 4 pi a 0 to r of r to the 4th dr. What's the integral of r to the 4th? That's 4 pi a r to the 5th over 5 from 0 to r, which is going to be 4 pi a r to the 5th over 5 coulombs. Again, that answer will vary depending on what that density is, right? The key part is assembling that integral together and being exposed to the idea that spheres can be cut into onion layers. Where we take advantage of a radial symmetry. We can find the volume of one of these little tiny pieces of the whole onion we can add together to find the big one. Okay. How many different ways are there to cut a cylinder? Where do most people end up dealing with cutting cylinders? In everyday life. Cake. Everything comes back to food. Right? Okay? When you go to cut a cake, most people cut wedges out of the cake. You cut squares. Do you like cut tray bakes or like, I'm talking about like a round cylindrical cake. You still cut squares? Good for you. Right? Because mathematically the best way to cut a cake is not to cut it into wedges. If you want to find out the mathematical best way to cut a cake that does two things, not only gives everybody the same volume of cake, but also preserves the cake's texture and moisture, go to YouTube, number file, best way to cut a cake. Number file is one word, okay, best way to cut a cake. Number file channel is fantastic, okay? They will show you mathematically the best way to practically, not stupid math where it's not practical, but a practical way to cut a cake so that everybody gets the same amount and preserves the texture and moisture while you're refrigerating it before the next cake binging episode. So let's talk about ways to cut a cake, because it's exactly the same way that we cut cylinders. The picture I have up there is one way you could cut your cake. In fact, if you've made cake, you know this is how you assemble your cake, right? You bake layers, and then you stack the layers on top and frost it, right? So that's one way to cut a cake. You could make a cake and then just cut horizontal cuts through it. Everybody get, some of you are like, that's my next party. Okay? So, let's see what we would need to be able to take advantage of this kind of like adding up charge, okay? So let's say that we had a cylinder that had a surface charge density. Surface, this is interesting, of a constant plus another constant times z. This is your first time seeing cylindrical coordinates, don't panic. The picture's right there, right? The z-axis right up there, okay? Z runs this way, okay? There are we got x's and y's and all that kind of stuff. We can do thetas and phis and a bunch of other things. But really, z-axes run along the length of the cylinder is what they do. Most usually, okay? And that's not an R, but that's supposed to be a sigma. Sigma, there we go, better sigma. All right, what are we looking for? Charge, how are we gonna find it? Integral dq, all right. I've given you that this is a surface charge density. So what do we know about sigma? It's Q divided by area. So we're trying to find the charge that's like on the outside of like a toilet paper roll, right? The cylinder. Not solid per se, but it could be, okay? All right, so that means that my dq, taking a little bit of a shortcut, is going to be sigma dA. Hopefully by now you're sort of falling into this routine of, oh look, it's a density and it's always going to be my density times something equals dq, right? So if it's volume, it's rho dV. If it's linear, it's lambda dl, dl, right? And now with surface area, it's going to be lambda dA, or sigma dA. All right. So again, the question of the hour is, how do I break it up? How do I cut it up, right? How do I find a surface area of a cake layer? I want just sort of the outside strip. I don't want the whole volume. I just want the surface area. How is the charge changing? What direction is it changing in? Z. So I know that this dA is going to have a dz in it somewhere, right? That's what I want. That's what I'm going for. It's how my function is changing. So I know it's got to have a dz. So how many more dimensions do we need to make a surface area if we've already got one? We just need one more. So what shape can I use for that outside strip? The circumference of a circle, right? If I take the circumference of a circle and I bump up, then I'll get a surface area, won't I? What's the circumference of a circle?
2 pi r.
2 pi r. So it looks like my differential area is going to be the circumference of a circle times a height. That'll give me a surface area. So that's going to go in there. This is the integral of sigma 2 pi r dz. Since my direction dz, cutting this thing vertically, what are my limits? Where does it start? Starts at the origin and goes to the length of my cylinder. I can go ahead and plug in my sigma function, a plus bz, and 2 pi and r dz from 0 to, that's supposed to be an integral, there we go. Okay, and this looks like it comes out with 2 terms in it, right? The a plus bz. I really don't want to like belabor this, okay? But what is a constant sitting here, right here in this integral? The 2 pi r is constant everywhere, right? R doesn't change with z. So I can pull that out, and now I've got a plus bz dz, which looks a little bit easier, doesn't it? Okay. And I'm just going to skip over all this. This ends up as 2 pi r times al plus bl squared over 2. Cool. I don't do integrals in here, per se. Okay. I set up a lot of integrals. You guys get to do them. All right. One way to cut a cake into its layers. What if, do I have a picture of this one? Yes. What if instead we go for the standard way of cutting cakes, which are these wedges? What's changing as we go around one of these wedges? It's an angle, right? The height's not changing, right? The radial distance isn't changing. What's changing, okay, is this angle as it goes around. So, this would be useful if we had charge densities, like a surface charge density that goes as maybe the cosine of the angle. So as we work our way around this thing, the charge is like positive and negative, following a cosine function. It's a pretty interesting charge distribution. All right, we want the charge. We're going to get it by integrating. We're going to get it from a sigma dA. And so the question now becomes, what is this A? We know we want a d theta. We know we want to change as we go around an angle. Okay? How do I write an area that represents the surface area, just the outside strip? I don't need the total volume of the wedge. I just need the outside strip of that cylinder. Okay, we know it's going to be height L, don't we? How wide is it going to be? Arc length. As if this day couldn't have got any worse. Right? Now we have arc lengths involved. Arc length is r theta. Right? So a change in arc length. In this case, are we changing the radius? We're changing the theta, aren't we? So this is going to be LR d theta. Check the units. What are the units of L? Meters. What are the units of R? Meters. Uh-oh, that's a meter squared already, isn't it? What are the units of theta? No units. Angles, radians or degrees. Those are just labels. They're not units. They're unitless things. Okay? A radian is has no units. Okay? So I end up with a meter squared out of that. Feeling pretty comfortable. So that goes in there. What are my limits if this is an LR d theta? 0 to 2 pi. You don't want to work in degrees if you can avoid it. Okay? But 0 to 2 pi definitely works because we're going to go all the way around to find that surface area. I can plug in my surface area function. That's A cosine theta times L times R times d theta from 0 to 2 pi. What's the constant in this integral? LRA. What's the integral of cosine theta? Sine theta, right? Is there a negative sign? I don't care. Sine theta evaluated from 0 to 2 pi. What's the sine of theta at 2 pi? What's sine of 2 pi rather? 0. What's the sine of 0? 0. What did I just get? 0? I took a cosine function, wrapped it around a cylinder, and went around once. Cosine, the charge went as the cosine, which means it spent half of its time being positive, and the other half being negative. What happens when you have the same positive and negative charge on the surface? You have 0 net charge. We just found a really complicated way of writing 0. brains? Are you like lost? Yeah? Yeah, good. That's good. Because this is the first time you've seen it. It's going to take your brain a little while to come to grips with it. Tomorrow in lab together, we're going to come to grips with it more. I've got a couple more examples of this to show you, and I'll do that in lab. I'll record it, don't worry. And then we're going to tackle problem number 4 from that math review. See you tomorrow. There will be time tomorrow to work on homework. There will be time. Bring your devices, bring your laptop. You'll have time tomorrow to get help on your homework.